So in this particular video, we are going to discuss about the infinite square well derivation of the ground state energy using the variation principle. We have used the same for the delta potential and for the harmonic oscillator, but this is going to be quite different from that. How? So let's see. So in the case of the harmonic oscillator and for the delta potential, we have choose our this particular wave function, which is equals to a e to the power minus b x square. But this is not valid in infinite square well. The reason behind this is that it will give you some of the infinities value for the potential, which is not true. So the infinite square well case is like that there are two walls, particle is within this wall, and the potential here outside the wall is infinite, and inside the potential is equals to 0. So when you will use this trial wave function, you will get very different values, even infinite values, which do not accord with the idea of this particular infinite square well. So that's why we don't have to choose this particular Gaussian wave function. In this particular video, we are not going to choose any trial wave function to derive the ground state energy, because we are going to use another very beautiful thing in this particular video, which you can use for the harmonic oscillator and for the delta potential also. Okay, so the thing is that you will study in the quantum, there are methods to do this for the wave function method, but by doing your trial wave function, all that stuff in infinite square well, it is quite lengthy. Okay, not hard but a lengthy method, so that's why I'm not going to use that. This in this particular video, a very short method, not more than 5 to 6 line, we are going to derive the lowest energy of the infinite square well. How? So we all know, it means I'm hoping you know that the quantization rule tells us that the integral from x1 to x2 of your momentum dx is equals to the n pi h bar. Okay, so well, if you haven't studied this, I will make a video on this, but you have to remember that this is the quantization rule in the quantum mechanics. Here this is the classical momentum, here this is the classical momentum, okay, not the quantum momentum, and the formula of this classical momentum is root under 2m e. So here this momentum is constant. So when you will do this particular integral, let's see how we are going to derive this. So if you put down the value of momentum as a 2me, as energy is not a function of x, so this momentum is constant, we can take it out from this integral. And the limits here, how we have to how we have to choose. So the limit is like that, from 0 to L, length of this particular well is L, from 0 to L. Okay, now if you will do this, you will get as a root under 2me and the integral of dx from 0 to L, and here n pi h bar. The derivation of this, I'm going to do this in the another video. Okay, when we will discuss about the WKB approximation, you will see this particular rule, because this is very useful in deriving the approximate solutions of the Schrodinger wave equation and its energy. Okay, so then this is equals to the root under 2me. This is a very easy integral into L, and it is equals to n pi h bar. Okay, now doing the squaring on both side, you will get this as 2me multiplied by L square is equals to n square pi square h bar square. Okay, so energy we equal to n square pi square h bar square divided by 2ml square. Yo, we have derived it. You can see that how short this method is, and this is the exact solution of the energy state for the infinite square well. You see how we have derived this using this particular very important rule, and the derivation of this rule is also quite important. You have to do this, but you know how this is very simple. It will take more than 5 to 10 minutes while deriving it the lowest energy with the help of the wave function. But using this method, you can see that it can be done in not more than 1 or 2 minutes. Okay, so this is a very easy derivation. You can try this method also in the harmonic oscillator. You have to try this. You will see that how this method is very useful. So this is our video. You can see that how short this method is, and this reduces our video length also. So this is our today's video where we have derived the infinite square well. You can say that this is quite a trick to derive this of the ground state energy. And if you want to know about the wave function method, that how to derive this from the wave function, you can say Griffiths. You can see the Griffiths. Okay, so in Griffiths quantum mechanics, the derivation is using the wave function. Okay, and in Griffiths quantum mechanics, this rule is not quite used, not widely used, you can say that, in Griffiths quantum mechanics. So this method is given in the book. If you want to follow a book side by side, the book is in the Noradin Zetley, I guess this is the spelling. Yeah, this is the spelling, Noradin Zetley Quantum Mechanics. This is a book, I will say, more advanced than the Griffiths Quantum Mechanics. It discusses various types of things other than the normal things that are given in the Griffiths Quantum Mechanics. So this will more mathematical than the Griffith. So Noradin Zetley, you can see the derivation of the harmonic oscillator and the also hydrogen atom ground state energy using this particular principle that I have used for the infinite square well. Okay, so this is for today's video. Thank you for watching the video.